Are you going yet?
Yeah.
Okay. I just want to get that picture. Okay, so here we go. We have get the water going. Hopefully it won't be splashing in too many directions other than just straight down. Okay. So if we envision this as a magnetic field going down from north, notice all of these have a north on them. Imagine the South Pole is down here. Well, if I take that as a loop of wire and I put it into the magnetic field, you'll notice that I have maximum amount of magnetic field going through the loop versus this. Agreed? Right now the magnetic field is going parallel to the face of the wire. This is the face of the wire. This right here, we have maximum magnetic field going through the wire. Can we all see that? Okay. Right now here I have no magnetic field going through the loop. Maximum, minimum, sum. So right now it's going from minimum to a maximum. Now it's time for us to use the words. The word that they use here is magnetic flux. Flux, unfortunately in the vernacular, flux means change. Here it doesn't mean change. So again, imagine that magnetic field is going down again. Right now I have maximum flux in that loop. Minimum flux. Maximum flux. Okay? Flux is defined as magnetic field times area. Turns out the electric flux is the same way. Electric field times area. Do we follow that? Okay, so right now again, that would be maximum, minimum, etc. What if the magnetic field were going this direction? Well, let's just say the magnetic field is going, for me, or I guess for you guys, that would be the negative x direction, yes? The magnetic field is going this direction. And if this is flat against the y axis, the amount of flux in the loop is maximum. If it's flat with the x-axis, it's a minimum. Pause, please. Once again, if this is the direction of our magnetic field, we'll draw that with a vector. And if our loop is this direction, okay, we have to define that loop. And the way we define it is with the normal to the loop. Actually, I'm going to switch this around just to make this easier. Say the magnetic field is going up, and this is normal to the loop. Meaning, here's the face of the loop, and there's the normal to the loop. And it changes like this. Everybody understand what I'm doing there? Why would we do that? There are two ways to define this loop. You could say the direction of the loop is flat with a loop, coming out of the board. Well, if you're going to multiply two things, I'm going to multiply B times A. Your next question at this point should be, does that give me a scalar or does that give me a vector? And the answer is it gives me a scalar. This gives me something known as the magnetic flux, which is a scalar and has the units, this is all in your book, has the units of Tesla, meters squared, or Webers. Okay? And if it's a scalar, and we're doing vector multiplication, are we using dot product or cross product? And the answer is dot product. So, that's our equation. That it actually looks like this. The magnetic flux equals B dot A, which we know equals the magnitude of B times the magnitude of A times the cosine of theta between them. That's also why, right here, you'll notice that the direction of the loop is defined this way, so that when they're parallel, you get the maximum. If it was a cross product, we would define it this direction, so that when they're perpendicular, you would get a maximum. Okay? And yes, as this thing rotates from here, and let's imagine it starts to open up, and it's coming, that's hard to draw three-dimensionally, but it's coming more towards us, and finally it's like this, and the area is facing towards us. Now the flux would equal 0. Here the flux would equal BA cosine theta. Here the flux would equal B times A, because the cosine of theta is the cosine of 0, which is 1. Stop.